In the chem activity number 6 and the corresponding videos, we once again explore further the concept of the mole. We will look at the molar mass of molecules, how to calculate it. We'll also look at the mole relations involving molecules. The intended learning outcomes are to describe the mole concept, apply it to calculate the number of particles and the amount of substance in moles. Define the term molar mass and calculate the mass of 1 mole of a species, whether that be an element or compound. And given the mass, determine the amount of substance in moles, or given the amount of substance in moles, determine the mass for an atomic or molecular element or for a compound. We'll start by looking at what's involved in calculating the molar mass for a molecule. In the chem activity 5, we saw that the molar mass is the mass, of course, of 1 mole of particles, and in particular we were looking at elements. When we turn our attention to a molecule or a compound, it's simply understanding that a molecule or compound consists of more than 1 atom, and therefore we need to consider the mass of all the atoms that make up that compound. So here I've shown a molecular representation of a molecule of ethanol. The white balls represent hydrogen, the gray balls represent carbon, and the red ball represents oxygen. Simply by counting the number of hydrogens, the number of carbons, and the number of oxygens, we can determine the molecular formula, which would be C2H6O. Of course, the subscripts indicate how many of each of the atoms are in the compound. In order to calculate the mass, and in this case, we're going to start off by calculating the mass of a single molecule. The idea is that we know that we have 2 atoms of carbon in that molecule, 6 atoms of hydrogen, and 1 atom of oxygen. And therefore, we would multiply the number of atoms by the corresponding atomic mass of each of the atoms. And so, of course, we have a certain mass of carbon, hydrogen, and oxygen in atomic mass units. And then we just add them all together. The molecular mass for ethanol would be 46.069 atomic mass units. But often, of course, we don't deal with single molecules. We like to work with moles of molecules. It's a very easy transition to convert all of this to moles, because instead of looking at the mass of 2 atoms of carbon, we'll look at the mass of 2 moles of atoms of carbon. And so that's shown in the next part of this calculation. So again, it's the same molecular formula, but now it's the mass of 2 moles of carbon atoms, the mass of 6 moles of hydrogen atoms, and the mass of 1 mole of oxygen atoms. So the calculation looks almost identical, except now this is 12.011 grams per mole of carbon atoms, not 12.011 atomic mass units. We do all the math, and in fact we come up with the same number, 46.069 grams. Of course, this is per 1 mole of ethanol molecule. As it turns out, therefore, we can consider that the molecular formula represents, in a sense, a conversion factor. It tells us how many atoms or moles of atoms of each of the different types of elements that are in the compound. So, for example, as I say, the molecular formula represents a conversion factor. We can say there are 2 moles of carbon per 1 mole of C2H6O, or 1 mole of oxygen per 1 mole of C2H6O, or, of course, 6 moles of hydrogen per 1 mole of C2H6O. I'd like you to give a little bit of practice in calculating molar mass, but before we do that, I'd like to show you a picture representing something that would have happened, let's say in the mid-1800s, because I'd like you to be calculating the molecular mass and the molar mass for diethyl ether. Now, diethyl ether and chloroform were used as anesthetics in the mid-1800s. You can see that there's perhaps someone that's supposed to be a doctor, and he's getting his patient to inhale, presumably, some diethyl ether. The idea is that this would put the patient to sleep or render the patient unconscious, and then the doctor would do the procedure. Normally the procedure would have inflicted a lot of pain, but of course if our patient is unconscious, they don't feel the pain. This is an early example of an anesthetic. One of the unfortunate outcomes, of course, is that diethyl ether and chloroform are both toxic, and they would do serious damage to the liver, for example, of the patient. Fortunately, we have better anesthetics these days. So I ask you to look at exercise number 1, 2, and 3 in relation to looking at this ball and stick representation of diethyl ether. You may wish to pause the video while you do this. So of course we can easily come up with the molecular formula by counting the number of atoms as represented by the ball and stick. And there are 4 carbon atoms, there are 10 hydrogen atoms, and there's 1 oxygen atom. So this would be the molecular formula. Again, this is a kind of conversion factor that tells us the number of each of these atoms in one molecule, or the number of moles of these atoms in 1 mole of molecule. First of all, to calculate the mass of 1 molecule of diethyl ether, the calculation would look something like this. So we've got 4 atoms of carbon, 4 times 12.011, 10 atoms of hydrogen, 1 atom of oxygen, and then the corresponding masses, and then we, of course, just add them all up. In terms of significant figures, because of the hydrogen, we're only allowed 4 sig figs, and therefore the final mass is 74.12 atomic mass units. Again, we don't normally work at the level of 1 molecule, and therefore we can think of moles of molecules. The calculation would be essentially identical, in that instead of 4 carbon atoms, it's 4 moles of carbon atoms, 10 moles of hydrogen atoms, 1 mole of oxygen atoms. You can see that we end up with the exact same number, that is 74.12, but now it's grams per 1 mole of the diethyl ether molecules. Now, I'm showing you a more formal way to do this calculation. Often what students would do, and what I would do, is just do the calculation right on top of, let's say, the molecular formula. So I don't need to see this full representation. So in other words, we could write something like this. So I know that I've got 4 moles of carbon, and therefore I might write 48.044 grams on top of the carbon. I've got 10 moles of hydrogen atoms, so therefore I'd write 10.08 grams for the hydrogen, and then I've got 1 mole of oxygen atoms, so I'd write that in here, and then I would just add them all up. Okay, I've got 74.12 grams per mole. Because usually this calculation is part of a more significant calculation. So again, you don't need to be so formal.